Okay, let's talk about the regioselective reactions of epoxides. So regioselective, this is a new phrase for you. And so basically what the term regioselectivity means is we can select the region of the substrate that we attack, okay? And so typical question on the exam is I'm going to give you a non-symmetrical epoxide where you're going to have one carbon here that may be primary, and then the second carbon over here is going to be secondary, or I'd give you a secondary and a tertiary, okay? And so what you need to know is based on the reaction conditions, okay? We're doing something a little different here. We're not doing a substitution reaction, we're doing a nucleophilic addition. And so when we talk about a nucleophilic addition, we're going to talk about the nucleophile either adding, okay, to the more subbed or the least substituted carbon, okay? And so under basic conditions, what we observe is that my nucleophile will attack the least substituted carbon. And under acidic conditions, the nucleophile will attack the more substituted conditions, okay? And so under basic conditions, we need a good, strong nucleophile. But under acidic conditions, we can have a poor nucleophile. And I'll go into the whens and whys in class. But in general, what's important is that you do this mechanism, you know the regioselectivity, okay? And that you be careful when you're drawing your bonds. Okay, so how do you know if something is basic and how do you know if something's acidic? Well, I don't know what else to tell you, but you know, typically when you see an anion in a metal, okay, so if you see a metal, okay, plus an anion, we're going to assume it's basic, okay? Conversely, if you see H plus, you're going to assume it's acidic, okay? Now, this is kind of new to us, right? Where we typically see the nucleophile above the arrow and then we see the solvent below the arrow. But now what we have here is we have this 1 and then 2. And so this is a two-part reaction. And so we're going to assume, okay, that part 1 happens and then we add the water. In other words, we don't have this lithium ethoxide in solution with the water. Okay, we're going to let the lithium ethoxide attack the epoxide, and then we're going to do what's called a water workup. Okay, we're going to do what's called a water workup. And so as far as nucleophiles go, okay, this is a relatively good nucleophile. Actually, it's pretty good. And just like I taught you before, we're going to ignore the metal. Just cross it out. And so you know when you cross out the metal, you have what? You have this negative charge here. And so the way this happens is I have nucleophilic attack of the least substituted carbon. Okay. Once that happens, epoxides are relatively stable, but they're also highly reactive due to ring strain. And so once that happens, what we're going to do is we're going to pop open this bond. We're going to break this bond and pop open the epoxide. Now, we're doing a ring opening reaction. And so it's very common that students drop carbons on these. And the biggest mistakes I've ever seen with epoxides is the students will drop carbons. So when you go to redraw it, make sure that you don't drop any carbons. So 1, 2, 3. This is going to be my new bond. Between my least substituted carbon and my nucleophile. Of course, once I open up this bond, okay, this oxygen is essentially my leaving group, okay? That oxygen is essentially my leaving group. And just like we saw before with the leaving groups, right? The leaving group takes the electrons that are in the bond with it. So now I have this anion. We can't complete a reaction with a charged species, because by definition, it is not a compound. Compounds are always, always, always neutral. Okay. And so this is where the water workup comes in. So we're going to bring in an equivalence of water, and we're going to protonate my anion. Okay. And then the final structure will look like this. And that is your answer. Okay. Now, again, acidic conditions are different. Okay. Basic conditions, we're going to attack the least substituted. Under acidic conditions, it's a little bit different. Now, we're going to treat the oxygen in the epoxide the exact same way we did the oxygen in the alcohol, the oxygen in the ethers. Anytime I have a strong acid, which we have a strong acid, if I give you H+, what we're going to do is we're going to do protonation first. And so now what I have is I have this protonated epoxide, which will give me a good leaving group. So again, the leaving group in any epoxide reaction is going to be the oxygen atom. Okay. Before, up here, the leaving group was my oxygen atom, and now down here, my leaving group is going to be my oxygen atom. Now, something that we see under acidic conditions, okay, we start to see a transition state species that looks something like this. The bond between the more substituted carbon and my leaving group starts to break. I form what's known as a pseudo carbocation. And so what's happening now is I'm getting a rather large partial positive charge. Okay, and keeping in mind that my nucleophile, even though it's not charged on that oxygen atom, is a partial charge, partial negative charge. And so what's happening here, this partial negative charge here is being drawn to this charge right here. Okay. Now, again, this is kind of a side note as to why we see this type of regioselectivity, right? Under basic conditions, there's nothing special here. So it goes what? Under basic conditions, it's just going to go through the path of least resistance. In other words, the path of least sterics, right? But under acidic conditions, the oxygen-carbon bond starts to break, and we start to form the pseudo carbocation. Now, it's not an actual carbocation, but a lot of the electron density is being pulled away from this carbon right here. So, of course, it's going to be more stable if this starts to happen at the more substituted carbon, because then his neighboring carbon buddies can help him out with a little bit of hyperconjugation, a little bit of the inductive effect. Okay, so after protonation, we're going to see nucleophilic attack. So I'm just going to scoot this down here. After protonation, we're going to see nucleophilic attack. My alcohol is going to come in, attack. My leaving group is going to leave. Don't worry about stereochemistry until next chapter. Sorry, chapter 12. Okay. Paying attention. Actually, let me redraw this. Okay, so what I just did is I just flipped that methyl group up. So again, 1, 2, 3. 1, 2. Oops. 1, 3, and 2. Okay. The new bond that I just formed is between the oxygen. So the hydrogen and the ethyl just came along. Okay. And then another equivalence of ethanol will come in and deprotonate this. And then my final product would look like this. The bond. Ethanol. Okay, and so again, the biggest difference is what? If you look at my basic, okay, if you look at my basic addition, I added the ethoxide to the least substituted. Under acidic conditions, I added the ethoxide to the more substituted. So again, I mean, ultimately, we're adding an equivalence of hydrogen and an equivalence of ethoxide. But based on our reaction conditions, we can control where this is going to be added.